Good morning. I'm Devasena. In this lecture, we are going to discuss about the topic Doppler effect. The Doppler effect was first described in 1842 by Austrian physicist Christian Doppler. When sound is emitted from an object, it will have a particular wavelength and frequency. The wavelength will seem to change if the object is moving towards the observer or away from the observer. Doppler effect representation is shown here. In this diagram, we are seeing that object is moving towards the observer and it is moving away from the observer. Due to this movement, the change in wavelength occurs. Let us see another Doppler effect representation. In this diagram, in one side, the ambulance is approaching the observer. Due to this, observer hears siren with a high frequency. In the other side, the ambulance passes away from the observer. Due to this, the observer hears the frequency of the siren become lower. Before going to see the Doppler effect functions, let us see what is the sound wave. Sound wave is a physical phenomenon by tiny fast movements called vibrations that transfer energy from one point to another. These vibrations are transferred to the air medium and propagated in all directions in the form of waves. All sources of sound wave have some part that vibrates. Sound waves are longitudinal waves. There is no sound in vacuum, but the sound wave vibrates in air and in other places. Basic classification of sound waves. Sound that is below the range of human hearing is called infrasound. It is the range of frequencies detected by seismographs in detecting earthquakes. These waves can cover long distance with little obstacle. Animals like bats and dolphins generate ultrasonic waves and use the reflection of these waves to find their way. Hence, they can fly about avoiding the obstacles. Let us see the definition for the Doppler effect. This Doppler effect, where there is an apparent change in frequency and wavelength of a sound wave due to the relative motion between the source of the sound and the observer, is called Doppler effect. The Doppler effect is observed whenever the source of the waves is moving with respect to an observer. The Doppler effect of a moving sound source is represented here. The wavelength will increase and the frequency will decrease if the source is moving away from the observer. Here is the representation. In this diagram, the source is moving away from the observer. Due to that, the wavelength increases and the frequency decreases. If the source of the wave is moving towards the observer, then the wavelength will decrease and the frequency will increase. Here is another thing. In this, the sound wave is reaching towards the observer. Due to that, the wavelength decreases and the frequency increases. Expression for Doppler frequency. Let us assume a source sends out a sound wave that moves out at a speed of sound. Consider the stationary observers 1 and 2 located at either side of the source at rest. Each observer hears the same frequency produced by the stationary source. It is important to realize that the frequency of the sound wave emitted by a source does not actually change. Now consider the source is moving and emitting waves through a medium with an actual frequency f suffix s. Then a stationary observer relative to the source detects wave with a frequency f naught is given by f suffix 0 is equal to fs open bracket v plus or minus v naught divided by v plus or minus v suffix s. Consider this is equation 1 where f suffix s is the frequency of the sound waves, f naught is the frequency perceived by the observer, v is the velocity of the sound waves, v naught is the velocity of the observer, v suffix s is the velocity of the sound source. Here the symbols plus and minus indicate the direction of the relative motion of the source and the observer. The plus or minus sign is selected according to the relative motion between the sound source and the observer. When the source and observer are approaching to each other, V0 and Vs are positive, otherwise they are negative. One should notice that the motion of the observer and a source has different effect on frequency change. Doppler effect representations are shown here. Here is another representation. The apparent frequency due to Doppler effect for different cases can be discussed as follows. Case 1, stationary source and stationary observer. Case 2, moving source and stationary observer. Case 3, stationary source and moving observer. Case 1, stationary source and stationary observer. In this case, V0 is equal to Vs. Hence, equation 1 becomes F0 is equal to Fs. Consider this is equation 2. Here, the frequency as measured by the observer is exactly the same as the frequency emitted by the source. Hence, no Doppler effect takes place if there is no relative motion between the source and observer. Source and observer are at rest. A representation is shown here. In this diagram, both the source and observer are at stationary condition. So the frequency f is equal to v by lambda. Wavelength, that is the lambda, and the frequency f of the sound waves emitted by the source and are moving with the velocity v. Case 2. Moving source and stationary observer. Let us assume a source moves with the velocity v suffix s towards the stationary observer. When the source starts moving, it also starts producing sound waves, and these waves travel towards stationary observer in the air medium with the velocity v and frequency f suffix s. Here, the waves are compressed together and have a shorter wavelength and higher frequency. In moving source and stationary observer, we are going to discuss two cases. Case 1, when the source moves towards the stationary observer, then its velocity is negative. Then we have v suffix s is equal to minus v suffix s, and v naught is equal to 0 because the observer is stationary but the source is moving towards the observer. Consider this is equation 3. Hence, equation 1 becomes f naught is equal to f suffix s open bracket v divided by v minus v suffix s. Consider this as equation 4. Source is moving towards the observer who is at rest. In this, the source is moving towards the stationary observer. The value of the lambda dash is equal to v minus v suffix s divided by f, and the value of f dash, that is the change in frequency, is equal to v divided by v minus v suffix s into f. The motion of the source that is moving with the velocity v suffix s relative to the observer alters the wavelength lambda dash and lambda double dash and frequency f dash and f double dash of the sound waves. Case 2. When the source moves away from the stationary observer, then its velocity is positive. That is v suffix s is equal to plus v suffix s and v naught is equal to 0. Consider this as equation 5. Hence, equation 1 becomes f naught is equal to f suffix s open bracket v divided by v plus v suffix s. Consider this as equation 6. Moving source away from the stationary observer representation is shown here. The value of lambda double dash is equal to v plus v suffix s divided by f, and the value of f double dash, that is the change in frequency, is equal to v divided by v plus v suffix s into f. Motion of the source that is moving with the velocity v suffix s relative to the observer alters the wavelength lambda, lambda dash, lambda double dash, and frequency f dash and f double dash of the sound waves. Considering stationary source and moving observer case. Case 1. The observer is moving towards the stationary source. The observer is moving towards the stationary source. Its velocity is positive. Then we have v suffix s is equal to 0 and v naught is equal to plus v naught. Consider this is equation 7. Hence, equation 1 becomes f naught is equal to f suffix s open bracket, the numerator v plus v naught divided by v close bracket. Consider this is equation 8. If we simplify the equation 8 means we obtain f naught is equal to f suffix s open bracket 1 plus v naught by v. Consider this as equation 9. Stationary source and moving observer away from the source. Case 2. Observer is moving away from the stationary source. The observer is moving away from the stationary source. Its velocity is negative. Then we have V suffix s is equal to 0 and V naught is equal to minus V naught. Consider this as equation 10. Hence, equation 1 becomes F naught is equal to F suffix s open bracket V minus V naught divided by V. Consider this as equation 11. If you simplify, the equation 11 means F naught is equal to F suffix s open bracket 1 minus V naught by V. Consider this as equation 12. Here is a representation of observer is stationary, and we have three different sources representation. Stationary sound source. The other thing is source moving towards the observer. The third one, the source moving away from the observer. In both the cases, moving observer and moving source, if the source and observer are moving together, the frequency goes up. If they are moving apart, the frequency goes down. However, the amount that the frequency change depends on whether it is the source or the observer that is moving. Thank you very much for listening this lecture. If you like this lecture means kindly share this video to your friends. For further updates, kindly subscribe my channel. Thank you.